Hello student, the question says a point source of light is placed at the center of curvature of a hemispherical surface. The source emits a power of 24 watt. The radius of curvature of hemisphere is 10 centimeters and the inner surface is completely reflecting. The force on the hemisphere due to the light falling on it is. So let us try to solve this first in a very short method and then in a very lengthy method, like how we got the formula and everything. If you want the formula straight away for this, if it is perfectly reflecting, so if it is perfectly reflecting, so you will get the net force acting on this would be power divided by 2c. So power divided by 2c, what is the power given in the question? The power is given as 24 watt. So 24 divided by 2 into 3 into 10 power 8. So you will get basically 24 by 6 into 10 power 8. So you'll get 4 into 10 power minus 8. So 4 into 10 power minus 8. So the answer would be 4. But if you are like, how we got this derivation? What is the exact method to find this derivation? So let us go into the derivation part of this. So if you look at the derivation part of this, and in derivation also, first we will go for a simple derivation, a simple one. Then we'll go for the entire mathematically complicated one. So where we use integration and all that. Let us assume if a body is applying pressure in this way. Let us assume this is the pressure applied by a particle, and again another photon would come and hit the surface, and it is applying pressure in this way. So if pressure is acting on throughout the surface, we have seen a similar situation in surface tension concept where we find excess pressure inside the drop and all that. So if pressure is acting in this way, so because of all the pressures, in radial direction, radial direction means basically if this is the way, this is called radial direction, the net force will actually be pressure into, you have to take projected area. What do you mean by projected area? Okay, so we have to take only this area. This area is called as projected area. Like example, even though this entire thing is spherical, hemispherical, but the net force, if you solve it, you will only get pressure into projected area. That projected area is P into pi r square. If r is the radius of that, so it would be equal to uh, pressure into pi r square. Now, how we got this as pressure into pi r square, I will again do it at the end of this. But for now, remember that if you want a net force, this derivation usually we do it in surface tension chapter. But for now, just remember that if you have this situation, we can simply write net force equals to pressure into projected area. Once you understood this, let us find what is the pressure acting. We know pressure equals to force at a location, like force acting on a point divided by total area, that is 4 pi into r square. We will find what is the expression for pressure and substitute in this equation to solve the problems. So let us find what would be the force at a location. Suppose if this is the surface and imagine a single photon, it is traveling with a speed c, it travels and hits it and again bounces back with the same speed. So it is bouncing back again with the same speed c. So we know change in momentum is simply, if let us say this is positive p into I cap, I will take. So finally it is minus p into I cap. Originally also it is minus of p into I cap. So you will get minus 2p into I cap. For now, you will only take magnitude. So magnitude of change in momentum. So from here onwards, if I say that would be 2 into P. Here, P represents momentum of the photon. We know for a photon, by De Broglie's theory, we can write change in momentum is simply 2 into, so we know according to De Broglie, lambda equal to h by momentum. So using that, we will get momentum equals to h by lambda. So change in momentum, we got it as 2h by lambda. So if I substitute that, so change in momentum is 2h by lambda. So force acting on this due to single photon would be 2h by lambda into 1 by t. So this is the force acting due to single lambda. For power P at source, we have to find what are the total number of photons that are getting emitted. Because this is for one photon, we have to find what are the number of photons that are getting emitted for power P. Remember, for momentum also we are using P, for power also we are using P. So don't be confused by this. So if you say for power P at source, the number of photons would be, we know power equals to energy divided by time. Let us say n photons are getting emitted. So n into, in place of energy, hc by lambda equals to power into time. So the number of photons that are getting emitted is lambda by hc into power into t. Now once we know this, so the total force on the wall of a container would be, so F total would be 2h by lambda into 1 by t into lambda by hc into whatever is the power into t. So if I cancel the similar things, t would cancel it out, h would cancel it out, lambda also would cancel out, and we get F total is equals to 2 into power divided by C. So this is the total force like exerted for this power, for the given power. Now, as you know, this force will be acting if the entire photons that got emitted will hit a single point in a surface. But we know that since this is a hemispherical one at a distance, this force will actually be spread evenly in all the directions. So we have to find what would be that spread that would be present. So if we try to find the pressure acting would be F total divided by this force is distributed over 4 pi r square area. So 4 pi r square. So you will get 2 into power divided by C into 1 pi 4 pi r square. If I solve this, you will get power divided by C into 2 pi r square. But since it is already 2 pi r square area, uh, we are talking about the total area. Why? Because this power is distributed in the form of a sphere. It would be traveling in all the directions, even though the bottom part and topmost point are not present. So that's why it actually became pressure equals to force by F total by 4 pi r square. Again, I will repeat. Suppose if all these photons are hitting at a point, F total would be 2p by C. But we know the photons that are getting emitted are getting distributed in all the directions. So all the photons will not hit a point. If you take an imaginary hemisphere, how many, if you need to find the pressure at a location, pressure would be whatever force divided by total surface area of the hemisphere. So if I take total surface area of the hemisphere, this is what we end up with. Now we got the pressure. We will take this pressure and we'll substitute the net force acting on container equals to power divided by 2 pi r square into c into pi r square. So it would become power pi r square would cancel, and that's how we get power by 2c. So this is a way to solve the problem. If you are like you are confused with this derivation, because now I will further explain you an integration method to solve this, like why it would be p into pi r square. My suggestion is you just remember, whenever we have a bowl or anything like that and anything is reflecting and something like that, so net force would be pressure by pi r square, and you directly remember what would be the formula for pressure. So the formula for pressure would be power by c into 2 pi r square. So what are the formulas to remember? One would be net force acting on any spherical surface would be pressure into projected area. This is important. That means for given case, so pressure into pi r square, this is for given case. Suppose we have sphere on the top and sphere on the bottom in your ear. It would have become upper one projected area, bottom one projected area, then net force would actually become zero. Because this upper force would try to pull it upwards, this downward force would try to pull it downwards, and the net force would have been zero. And imagine we need only a part of this, not even a complete hemisphere also. Quarter sphere, and we need to find the net force acting on this. So the net force would be in this way. So we would have taken some other value, we would have taken pi r square by 2, become even slightly complicated. And what is the pressure formula for this? The formula for pressure that we got, it is power by 2 pi r square into c. So this is the formula for pressure acting at a location. So once we got, this is only for perfectly reflecting surface. I think if it is an absorbing surface, we will not get, we might get power by 4 pi r square into c. So I hope you understood the net force and pressure formulas. And from this, we will get, if we substitute both of them, net force would be P by 2C. So it is recommended for you to remember that. Now the question is, how is this net force become pressure into pi r square? How did it become pressure into projected area? Further, I will do again a big derivation. But if you are okay with remembering this formula, you can stop at this point. Let us try to look at the derivation part of that also. Suppose we have a point source that is emitting, and let us assume this is the pressure acting at this location. So let us assume due to that pressure, a small force dF is acting, and this point is at a value of theta and a small thickness of d theta. So it is acting at theta and a small thickness of d theta. So due to that, a force of dF is acting here. Now, if I resolve this dF into components, I will get on this side, if this is theta, we will get dF cos theta. On this side, we get dF sin theta. Similarly, here also there would be an exact point where which will give me dF sin theta and which would give me dF cos theta. So between this dF sin theta and dF sin theta would cancel each other. This dF cos theta would add each other. So the net force would actually be integration of dF into, like 2 dF into cos theta. Now, what are the limits of this? It is theta limits are 0. The least value of theta possible is 0. The largest value of theta possible is pi by 2. So we can write 2 would be outside integral 0 to pi by 2 df cos theta. Now, what is this df? df is nothing but if pressure is P, pressure into whatever is the area of the strip. I will call it as dA. What do you mean by area of the strip? Let me just show you. This is a small segment. So I'll show it in the next page. Suppose we have selected a small segment here. This is one, and we have one more segment here. We have selected a d theta segment. But if you notice it properly, this d theta is actually a part of a strip because it's a 3D surface. You can see, I'll just move it here. So this dA area would be present like a strip on the total wall of this sphere. That means there would be an invisible strip in this way with a small area of dA. So dA represents the total area of the strip. Since dA represents the total area of a strip, we can write P into. So if you draw an imaginary circle here, we have to find what is the radius of that imaginary circle. We know this is r, this is theta. So this one would be r sine theta. So dA value would be r sine theta into its small thickness would be r into d theta. So actual value of df, if I substitute integral 0 to pi by 2, so df value would be p into, it is r sine theta. So it would be 2 pi r sine theta. So 2 pi r sine theta into its thickness r d theta. If you are like, I'm not understanding this means, like this is slightly tough. You better remember the previous derivations only. So pi r square into sine theta into d theta into cos theta. So let me just substitute it in the next page. So we will get net force equals to pi r square into P. We get pressure into pi r square into integral 0 to pi by 2 2 sine theta cos theta into d theta. So I leave this integration to you. If you solve this pressure into pi r square, so you will get this value as literally 1. So since you get the literally the value as 1, or else since we have extended this video so much, I'll do this part also. Integral sine 2 theta into d theta 0 to pi by 2. Sine 2 theta is, so the differentiation of it would be minus cos 2 theta by 2, 0 to pi by 2. If I bring 1 by 2 outside, so minus cos pi plus cos 0 degree. So you'll get basically 1. That's how we get the net force on these kind of hemispherical situations as pressure acting into pi r square. I hope you understood how I have solved. As you can see, the video became very lengthy because we tried to derive each and everything. But if you don't need all these derivations, you can simply remember if it is a perfectly reflecting surface for a hemispherical bowl, EF net equals to power by 2c. Now, if you go back and if you want to know how do you want to get this power, how it became power by 2c. So we'll further try to derive the formulas in detail. F net equals to pressure into pi r square. How we got this as pressure into pi r square? What is the equation for pressure and all that? We have checked it in detail. And better you write the formula summary also for this case. Hope you understood how I have solved.